Now, the sag calculation. See, generally, as we discussed the steps before, then the rigid bus, all will be applied here, except the last couplers, because this is not a rigid construction. Instead of the couplers, here we are having the sag. In the rigid, it's an aluminum pipe, there won't be a sag. But here there would be a sag, because I am stringing the conductor between two support ends. Between two ends. So this conductor is free from other, in the middle, it is not having any support. It is free and it will move due to the wind. And the sag will increase due to the temperature rise, the length of the conductor increases. So if the length of the conductor increases, the sag will increases. If the sag increases, tension will increases. So all these conditions we have to consider when you are calculating the sag here. But fortunately, here in the substations, the span length means the distance between the this will be very, very low if I compare to the transmission lines. So there is no much required to calculate the sag here. Generally, all the developers will not do the sag calculation inside the substation unless specified by the client. That is also very, very rare. So generally, they will do with some rough calculation that they will maintain some 13 kilonewtons of tension on either side of this one, and they will finish the work. That's it. They won't do the sag calculations, everything. But as a design engineer, we need to know how to calculate this and what actually it is. Make sense, team? Shall we move? Any doubts till now?
No.
Yeah. Fine. So let me go to the presentation again. Just stop me wherever you are having a doubt. Yeah, fine. So as I discussed it before, for the rigid bus bar sizing, whatever the things we are doing, same, all the things will come like bus location, future expansion. Why future expansion? If the future expansion is there, it may show the effect on the towers, the tension. So I have to design the towers by keeping the future expansion in the mind. Next one is conductor selection. This already we know. And wind and ice loading, we have seen in the rigid bus bar sizing calculation. Same thing here. And they come to the insulator strength. Yes. 1 minute, team. Fine. Yes, sir. So first one is the insulator strength. The insulator strength, the suspension insulators generally selected based on the anticipated maximum loading conditions. The maximum loading for the porcelain insulators should not exceed the 40% of the mechanical electrical strength ratings. Generally, the maximum loading for the porcelain insulators should not exceed 40% of the mechanical and electrical strength ratings of those insulators, it seems. And the maximum loading on the fiber glass insulators may not exceed 40% of the manufacturer strength ratings. Generally, what they mentioned there for the insulators. This insulators is a suspension insulators, or it could be tension, so whatever it may be, post insulators. Next one is the span length. When I'm talking about the span length influences the conductor sag. As the span length is increases, sag is increases if the same tension is maintained. So to limit the sag, what I have to do? We have to increase the tension. So to increase the tension, I have to go for the extra design of towers, means a big towers. So sag and tension, strain buses are usually positioned above other substation equipment, what I discussed now. So the conductor breakage, if the conductor breaks, that could result in the equipment damage or outage. So to prevent this breakage and to avoid these accidents and to minimize the support structure size, the conductors are usually installed at tensions of approximately 13 kN. What I said before, or less than this. Sag may increases because of the deflection of the support structures. So generally, this is a rule of thumb. Generally, on all the substations, they will maintain this tension and they will close this exercise. So, and come to the temperature variations. As I again repeating here, if the temperature increases, sag increases, and if the sag increases and the tension decreases. Tap loads. This is a very important thing. Tap loads. What is this? See, now, as I said, as I shown you here, this is the conductor which is running on the top, and it has to connect to middle of the two isolators. So this is the tap from this. So this tap from the conductor to the buses or the equipment should be limited in tension to prevent the damage of the equipment. See, now what it doing? Let's see. Let's do some physics here. So I am applying a tension here. So tension here. I am applying a tension here. Some tension here. So two forces are acting like this, and it making it a some stride. But due to some loadings on this conductor is coming like this. But again, this tension, what I applied here, this is pulling this conductor to make it straight again. So if it is pulling these two, what will happen if I am placing some conductor here? The force now will act like this, right? This is the force of this tension. This is the force, and this is the force which is acting on the equipment. So this one is connecting to the bus or any equipment. So due to the forces acting, the connector which is connected to this equipment may damage due to these forces. So to restrict these forces, generally we install some slack connections. Slack connections is we are maintaining some support kind of thing between these things, like this. Support. This will minimize this one. So I am applying the force in this way. So it will minimize this effect of this pressure applied on this. So that's about the tap loads. It is very, very important. Sometimes it may be the most dangerous things for the lightning arresters in the substation. Fine. And same thing, the conductor sag, what we discussed it. So, but let's see the conductor sag here for this strain bus. In some cases, the maximum sag may occur during the most severe loading condition. For substation strain buses, the design tension, as I said before, generally we limited to 13 kilonewton per conductor under the most severe loading to minimize the size of the support structures. The conductor tensions have to be coordinated with the support structure designs to ensure the compatibility under all loading conditions. The tensions that will occur under unloaded conditions will be considerably less than the maximum generally. If I am talking about the light load conditions, where ice load is not there, it's like a tropical equator regions, the maximum conductor sag may occur due to the conductor temperature itself, where the conductor length is the maximum. This we discussed just before. And for other load conditions, sags we have to determine by considering the both high conductor temperature and also maximum loading on this. What is the maximum loading? Ice loading, wind loading, as well as the short circuit forces also. What we discussed in our last class. So these are the things for the conductor side. And this support in suspension insulators are there, right? See, I am stringing the conductor between the two structures with the support with suspension insulators. This suspension insulators will also add some conductor sag for the total sag. So this suspension insulator effect we have to calculate, and we have to find out what is the conductor sag due to the suspension insulator. And this we are adding with the total maximum sag, or if you are having the data from the manufacturers or sag templates, that will give you the total sag for your conductor. So based on this, you are choosing the tension, you are maintaining the clearances, and you are selecting the structures. So let's see the suspension insulator effect. Let's see this one. This is the figure you can see here. This is a suspension insulator, and this is the figure to calculate the sag due to the suspension insulator effect. This suspension insulator, if this is the conductor generally connected to the suspension insulator, this dotted line is the insulator catenary constant. What is insulator catenary constant? Catenary, what is meant by catenary? Catenary, it's a kind of a physics concept, physics term, that it's a kind of curve which will form due to the hanging of some wire or cable at both ends. That we will call as a catenary curve. This is called a catenary curve. Catenary curve. This catenary curve may exist for the insulator. This is the insulator catenary curve. And for the conductor, this is the conductor catenary curve. So, and this is some lengthy calculation. So no need to remember all these things. Just here what we are doing is, we are calculating the conductor strength. Sorry. We are calculating the sag here, which is Y equal to Y1 plus YC. Y1 is the insulator sag and YC is the conductor sag, which will gives us the total sag. Y is the total bus sag, including the conductor and insulator. So we have to calculate this. And now you can ask that insulator one, okay, this is the formulas. From this formulas, I got the insulator sag. How to calculate the conductor sag? The conductor sag will be calculated based on so many factors. Generally, in some cases, they will consider the maximum sag by the conductor. The maximum sag conductor formula is WL square by 8TT. This is the formula. This is the maximum sag. W is the weight of the conductor. L is the span length of the conductor. What is the span length? And T is what is the tension you applied on the conductor, like 2% of the UTS, ultimate tensile strength of the conductor, it seems. So if you place these things in this, and then you will get the worst condition of sag, means worst sag. There is a maximum sag. There is a maximum sag at could be that due to the temperature rise or due to the wind loading, whatever it may be, this is the worst sag. So this plus Y1 will give you the total maximum sag. So based on that, you can do the clearances and tensions. But also, if you want to do the optimization, this will give suppose a 7 meters of sag. 7 meters is the thing. But generally, 7 meters will not occur for your project. Maybe your project is located in a normal range of temperatures and ice loading. This might not be occurred. Suppose if you calculate the actual sag by using the sag templates, like what is the worst condition of the temperature at your region and what is the worst expansion of your conductor length, all these things, then you can find, suppose if you are finding 4 meters, so there is a 3 meters in distance, 3 meters is the some delta. So you can do the optimization on the tower height or the clearances or the tension, whatever it may be. This is again a separate subject. So what we have to find out in the strain bus, single simple sentence. One, we have to calculate the sag. That sag is due to the, maybe due to the conductor or maybe due to the insulator. The insulator effect, we have seen this. And the conductor sag, it depends upon the sag template or the temperature variations or the ice loadings and also wind as well as the short circuit force loadings, what we have discussed in the rigid bus bar sizing calculation. Same philosophy. So this is about the strain bus calculation. Clear, team?